Good afternoon, everyone. So today is lecture number 32, and the topic is basically on case or surface hardening of steel. So the name itself is suggesting that uh, we have to harden only the case of the steel, or only the surface of the steel will get hardened. Hardened means it will become stronger. It means the hardness will increase, or the strength of the surface will increase compared to the core. Right? So that means we can divide the entire steel on the basis of its surface and on the basis of its core, the center part. So basically here our priority is to increase the strength or increase the hardness of the surface only. Right? So that means you people have understood what is case and surface hardening. So case and surface hardening means hardening the surface only or hardening the case only. So what is the need of this? The second is what is the need of this? An example where this is essential. So suppose we have certain applications, like suppose just let me show you these things. These are few components. You can see these are few components which are basically used. This one. They are basically used in the automobiles. This camshaft, axle shaft, crank pins, gears, right? These are basically used in the automobiles, and this is a drill bit. You understand it is used for drilling rocks or something else. Basically, all are made up of steels. So here, the common thing is what you can understand. All these things rotates during its operation. They rotates, and due to these rotations of these components, they leads to the wear of the components. Wear means the material will get removed from the surface slowly due to the relative motion. Okay? Since this components rotates, so wear will happen. Slowly the material will get damaged. So now this is the situation, and if you understand, this is for these components also. Sometimes shock loading will be also there, right? Or there will be a sudden loading on these materials during its working, right? Or that is called shock load. So these are the two conditions, as I told. Okay, need of this. So need of this, I can write certain components. Filing, moving condition. Moving condition means they are in rotation. Rotation. Experience. Wear. And shock load. Or impact load, I can say. So this is one part, wear, and the part is the shock load. Okay? So that means now we have a situation. Now we have a situation where we need these components should have high wear resistance, right? Because wear basically starts from the surface. Wear means the material will get removed slowly from the surface. Finally, it may lead to the failure. So you understand now this one. Now we have a situation where wear is happening. So we have to what? We have to increase the wear resistance. So you remember, if a particular material have high hardness value, that means you can say that particular material have high wear resistance also, right? The material will not easily remove, because some people call like hardness is the resistance to scratch, right? And resistance to indentation also when you're applying load, any load, right? So that means wear will be not happening if the material have high hardness. So that, and you understand, wear takes place from the surface. So first criteria is what? To increase the hardness, surface hardness. So you can understand, that means if you have a drill bit, if you have a camshaft, axles, these crank pins, this axle shaft gears, right? These gears you have, everybody have seen, right? In your bikes, it is easily visible. So these things will undergo wear. So to protect them, we have to increase the hardness of the surface only, right? So I have written over here to increase the surface hardness. The surface hardness to increase the wear resistance. Of surface, right? Next one is, you can see there is another situation where these components will face what? Shock loading. They will experience shock load, very sudden loading, right? So in that condition, we need that material should have high toughness. So toughness will be provided by the core basically. So I can write increase the toughness of the core. Otherwise, the material may break easily. The crack may get initiated and it can easily propagate through the materials, right? So you people have understood up to this. That means these are the components which will experience wear at the surface, and it may undergo fracture due to shock loading. So we have to protect the material from fracture, and we have to protect the material from the wear. So to protect the material from the wear, we have to increase the surface hardness, and to protect the material from the fracture, we have to have a soft or tough core. Better to write tough. So that means in this material we have high hardness at the surface, and at the center of these materials we have high toughness. So that is the thing. So that is why we are doing case hardening or surface hardening. That means we are increasing the hardness of the surface or the case. Fine. Next is why we are doing that, because to increase the life of the moving component, rotating components. To increase the life of moving or rotating components, we have to increase the surface hardness. And that term is called case hardening or surface hardening. Then ways to do case hardening. So what are the different ways? So up to this, you people have understood, that means we have to harden only the surface. We are not talking about the core. Core will remain as such. So how to do that? How to harden the surface? So we can harden the surface by two means. If you remember, already we have discussed about the strengthening mechanism. So one kind of strengthening mechanism is the transformation strengthening, where we do transformation to the martensite, right? The martensite is a very hard end, wear resistance phase, right? So one way is to do what? One way is to do transformation strengthening. How? By by heat treatment, by heating and cooling of the surface only. So that means if people have understood, we have to do heat treatment. That means, right? We have to do heat treatment of the steel in such a way that it should be very fast, huh? In such a way that only the surface or up to certain depth from the surface that will get heated up and that will get cooled or quenched, you can say, and it will get hardened by formation of martensite, right? So one is do transformation hardening by, otherwise you can write by transformation strengthening. Repeatedly, huh? There is another way which we'll discuss in details, that is by changing the chemical composition of the surface only. Right? As I told, we are not bothered about the core, we are basically bothered about the surface. We have to increase the hardness of the surface or wear resistance of the surface, so we can change the chemical composition. So by changing the chemical composition. So surface chemical composition will change so that it will become harder or stronger. Right? So those are basically, one is carburizing, or I can write by introducing using carbon or nitrogen or both or etc onto the surface or the case of the steel surface of the steel. So this is one of the way, by introducing carbon or by introducing some nitrogen onto the surface of the steel, we can increase the hardness or strength of the surface only. Right? So this is not in your syllabus, but this part is there in your syllabus. So this part, the second part, this is also called thermochemical, right? Thermochemical heat treatment. You understand why thermochemical? Because thermo means heat is involved, that means heating and cooling is involved, and chemical means we are using some chemicals like carbon or nitrogen. We are not exactly using carbon nitrogen, we are using some source of carbon and nitrogen, right? Thermochemical heat treatment, right? Or in general words, some people call case hardening. So I can conclude here, the case hardening is basically hardening of the surface only. The core of the steel will remain soft or ductile, or you can say tougher, right? So this can be done by two ways. Either we do phase transformation on the surface only, just by converting it into martensitic microstructure, just by rapid heating and rapid cooling, right, of the surface only. Or we can do what? We can change the chemical composition. During heating, we can change the chemical composition of the surface so that it will become harder, just by introducing hydrogen, or mixture of those. But okay, fine. So there is a process called carburizing. So carburizing is nothing but a case hardening or surface hardening process. Carburizing is nothing but a case or surface hardening. Basically, it is thermochemical. Thermochemical heat treatment. right? And simply, if somebody will ask what is carburizing, carburizing is basically a surface hardening or case hardening process where we increase the carbon percentage of increase the carbon percentage on the surface of the steel only. We are increasing the weight percentage of carbon increasing the weight percentage of carbon, increase the weight percentage of carbon on the surface. That is called carburizing. It is just opposite to decarburizing. Decarburizing, if you remember, when we do normal heat treatment, the carbon will get removed from the surface. But here we are intentionally adding carbon to the surface of the steel. We want to increase the weight percentage of carbon of the surface layer of the steel or up to certain depth of the steel, right? Now, what is the procedure or what is the step? The steps is simple. We will take a piece of steel, and you have to remember for carburizing, we basically choose low carbon steel, right? Low carbon steel means it is the carbon percentage is nearly 0.25, right? Or below that. And here we will take the steel. So I can write low carbon steel. Low carbon steel, and you have to heat it in a furnace surrounded by the steel is surrounded by atmosphere of carbon. So the low carbon steel is taken and it will be surrounded by a carbon containing materials. Then it will be put inside a furnace and the temperature will rise. So this is the
Sir,
process. Yes.
sir, in which furnace is it possible to do this?
This furnace is possible means you can use normal muffle furnace, but the thing is what we need a like heat resistant steel actually. Heat resistant steel means heat resistance container. So where we in that container we will put our raw materials. Raw materials means steel with the carbon containing materials. Then we'll seal it. Then this heat resistant steel box will be put inside the furnace. The furnace here the furnace aim is to provide temperature. That's all, nothing else. And carbon containing materials means they will provide carbon, but this will be in the sealed condition. Suppose you take a steel tiffin box, for example. You take a stainless steel tiffin box. You take a small piece of steel, which you require to do carburizing. You put it at the center. You first put some charcoal or coal in this tiffin box, small granular form. Then you put the steel, which is you want to carburize, at the center, and you close the tiffin box and you put the tiffin box into the furnace and you rise the temperature of the furnace. I think you people understood up to this, right?
Yes, sir.
Yes. So you understand the source of carbon is can be liquid, can be solid, can be liquid, or can be a gas. Today only we'll discuss about the solid and liquid if possible. Fine. So basically the solid example, you understand, the solid carbon is coke or coal, right? Coal, charcoal, you can use coke, all these things. Basically we use granular coal, sometimes charcoal also. And in case of liquid, basically we use, for liquid basically use like some salts, cyanide, salts. These are molten cyanides also. And in gas, we basically use some natural gas or some hydrocarbons. Some natural gases which contain carbon. So these are hydrocarbons, right? So this is a setup you can see. This is actually, so that means you can understand we can have this on the basis of what kind of source of carbon we are choosing. Either we are choosing solid carbon, liquid carbon, or gas carbon. We can divide this carburizing into three categories. One is called solid carburization, liquid carburizing, and finally gas carburizing. So these are the three carburizing: solid, liquid, and gas carburizing. So you can see the setup here. So you can understand this is suppose a furnace. Okay, fine. This is not exactly furnace. Suppose this surrounding is furnace, for example. Let this white portion is your furnace, and this is a suppose heat resistant steel, this part, and inside this part we have suppose a piece of steel here, and we have carbon atmosphere here. This white portion is the carbon atmosphere. This is the steel piece, and this is the sealed part. That means heat resistant steel. Now we are heating. The furnace is providing heat. So basically we choose a temperature of austenitizing temperature. This is called solid carburization because we are using coal or charcoals basically. Right? Coal and charcoals are solid carbons, so they will provide carbon. So what will happen? The temperature will rise to the austenitizing temperature. Like I can say, okay, here I can write temperature is suppose 900 to 970 degrees centigrade. So this is the temperature basically. That means this is the heat. Up to this temperature will heat the steel box, and the time duration will be time duration or holding time. Basically we choose 7 to 8 hours, or it depends, you can make it more, because you have to remember this time is also important. Why this time is important? Because suppose you want to make you want to increase the weight percentage of carbon to a large depth, then what you need to do, you have to increase the time. Suppose you want to get a very small depth of hardness, then the timing will be less, right? So time will decide what is the depth of hardness, up to what depth from the surface you want to increase the weight percentage of the carbon, right? More time, holding time means up to more depth the carbon percentage will increase, right? So basically we choose like case depth will be like we choose 2 to 3 mm maximum. That means up from the surface to 2 mm or 3 mm we increase the carbon percentage, right? And this is basically, as I told, austenitizing temperature.
हेलो सर,
Yes.
टाइम ड्यूरेशन में यूनिट का कौन कौन सा?
Sorry, time duration.
यूनिट
Unit.
यस सर.
Hour.
ओके.
So can you people tell me which mechanism will take place? Which kind of metallurgical mechanism?
Diffusion.
Diffusion, obviously. Very good. So here diffusion is involved, right? So that means from the carbon atmosphere, the carbon will diffuse onto the surface of the steel. So more is the holding time, more carbon will diffuse, and it will diffuse to a large distance, right? And temperature is here, you understand, with rise in temperature, the rate of diffusion also increases, right? So can you people tell me why we choose austenitizing temperature for this solid carburizing? This solid carburizing is also called pack carburizing, because we are doing packing of coals or charcoals or this coke in a heat resistant steel with the steel piece. Can anybody guess why?
Because in austenite solubility of carbon is higher.
Yes, obviously, very good. You people understood, because we know that the solubility of carbon increases if we have an austenite phase, right? An austenite phase means if we are taking the steel to the this temperature 900 to 970 degrees centigrade, that means austenite will be there and solubility will be more, right? Suppose we will do this kind of treatment in ferritic resin at a low temperature, right? Suppose at 400 degrees centigrade. So what will happen? The process will be not effective because ferrite will be there. So what will happen? The solubility of carbon in ferrite is very low, but solubility of carbon in austenite phase is very high, right? So that's why we choose this austenitizing temperature. And temperature is also high means the rate of diffusion will be also higher. So diffusion of carbon from source to surface. So that means there is a carbon potential is available, right? Carbon is at high potential at the source and carbon is at low potential at the surface of the steel. So obviously it will diffuse from high potential region to low potential region, obviously. Surface of the steel. Okay, let me tell you quickly some points so you understand. So pack carburizing or solid carburizing, here we use solid source of carbon, basically coal, charcoal or coke. Basically maximum people use coal, granular form of coal, and this will be done for 7 to 8 hours basically. And the case depth also depend upon the holding time, and this is done in austenitizing temperature because solubility of carbon is more in austenite region or in austenite phase. And basically we choose, as I told, low carbon steel, right? Carbon content should be maximum 0.25. We can by this we can increase the carbon percentage like up to 0.7 to 0.9 weight percent. So we can increase the weight percentage of carbon up to like 0.7 to 0.9. 0.7 to 0.9%. That means suppose starting carbon at the surface is 0.25, we are increasing up to 0.7 to 0.9. And we understand the hardness basically is directly proportional to the weight percentage of the carbon, right? But up to certain limit, right? Certain limit. Like suppose we have a plain carbon steel, only plain carbon steel. We want to increase the weight percentage of carbon. So if we increase the weight percentage of carbon up to 0.8, the strength will increase, sorry, hardness and strength will increase. Basically, we are talking about hardness means hardness will increase. But when the carbon will be more than 0.8, again the hardness will decrease. Right? Similarly, suppose we have a uh, carbon manganese steel. Carbon and manganese also present in a small amount, right? So in that condition, what will happen? The If you increase the carbon percentage up to 0.8, the hardness will increase, but up to also like 0.85 or nearly towards 0.9, the hardness will still increase. But after that, again it will fall. The hardness will fall again. So in other words, I can say the hardness with respect to weight percentage of carbon is not same for all type of steel. It is different for alloy steel, it is different for carbon steel, it is different for carbon and manganese steel, or depending upon the alloying elements also. Right? So now if we are talking about the reactions happening inside this. Okay, before moving into that, let me talk something about the raw materials used. So what are the raw materials used here? The raw materials used here are, as I told, granular coal plus barium carbonate. So what exactly barium carbonate? Barium BaCO3, barium carbonate. It is already written over here, barium carbonate, right? So we take nearly 80% coal, granular coal. Suppose this is 80%. And barium carbonate, suppose 20%. So here barium, you understand the function of coal is to provide carbon. But what is barium carbonate doing over here? So what is the function of this? So barium carbonate is basically called, it is written over here, I guess. It is basically an energizer. It's act as an energizer. Barium carbonate 20%, it is act as a energizer. So now we'll see the reactions. What is the reaction happening inside the heat resistant steel box, which will increase the weight percentage of carbon on the surface of the steel, right? So that means obviously barium carbonate have some role to play, right? So you can see the first reaction. Barium carbonate, because the temperature is very high, you can understand, and this is a carbonate. So carbonate will undergo calcination, obviously, or it will undergo decomposition into oxide and carbon dioxide. So barium carbonate at high temperature will decompose into barium oxide and carbon dioxide. Now we have a carbon dioxide gas and we have solid carbon, coal, right? So they will start react. So this CO2 evolved during calcination of this barium carbonate will start reacting with the coal, solid coal, right? So this will give rise to 2CO, 2 carbon monoxide. Now this 2 carbon monoxide, which is a gaseous phase, will start reacting with the surface of the steel. So this is the iron, means this is the surface of the steel, right? So the reaction will finally give rise to iron containing carbon on the surface. That means the carbon percentage on the surface will increase, and it will give rise to CO2, right? Then again this CO2 of 10 will react with carbon to give rise to 2CO. So this process will continue. I think this part is clear, everybody. Now we have another process called liquid carburizing, because I told we are using a liquid source of carbon. That is basically a salt. Basically, we are using molten cyanide salt. Is used. That's why, because this is liquid, molten means this is liquid, and the source of carbon, so it is liquid carburizing. Fine. So we have to use a salt bath furnace to keep the salt in molten state. And we need cyanide salts. That is basically which kind of salts we are choosing for this. We are choosing sodium, potassium. It depends. You can choose sodium or sometimes sodium and potassium both. Or basically we choose sodium or potassium cyanide. It is a salt. potassium or sodium cyanide. And we also choose some activator, that is chlorides. Now, which kind of chlorides? Sodium potassium chloride. This basically we are using barium chloride, for example. Other chlorides are sodium and potassium. So here the main important part is the salt, that is cyanide and barium chloride. So you can see the reaction which is happening, and you have to remember the process is carried out at a temperature of 815 to 900 degrees centigrade. The temperature is basically 850 to 900. And the important point is, you remember the molten salt will be covered by graphite powder. Why? To reduce the heat losses, obviously. To reduce radiation losses. And to prevent excessive decomposition of salt. So these are the two main names. To prevent the excess decomposition of the salt and to prevent the heat losses by radiations, this molten salt will be covered by graphite powders. And barium chloride act as a, what I told, activator. So you can see the reaction. The reaction is not directly happening. First, barium chloride will react with sodium cyanide salt. This is the main source of carbon, which is reacting with barium chloride activator to form barium cyanide. And now barium cyanide react with iron and finally end up with iron containing this carbon. Okay, so this part is missing actually. So this part is BaCN2 actually. You can write this part is missing, FeC plus BaCN2. BaCN2. So this carbon is nothing but the carbon at the surface. Should not be confused. Here this carbon is also nothing but the carbon at the surface. Okay, so conclusion of this today's topic is what basically our main priority is to increase the hardness or strength of the surface. We can do carburizing process or carburizing heat treatment. In carburizing heat treatment, our aim is to increase the weight percentage of the carbon on the surface. We can go for either solid carburizing, we can go for liquid carburizing, we can go for gas carburizing, and there is another carburizing, we can go for vacuum carburizing. We can use vacuum also. Maybe we'll discuss in coming lecture. So basically, you understand in solid carburizing, the temperature is very high, like 950 or 970 or 930 like that. But in liquid carburizing, the temperature is less, up to 850 to 900 degrees centigrade. And in solid carburizing, we are using coal basically. But in liquid carburizing, we are using basically molten salt, cyanide salt, sodium cyanide. And solid carburizing, we are using an energizer to start the process, that is barium carbonate. This one. And for liquid carburizing, we need an activator, that is barium chloride. Right? Okay, I'll stop here. We'll continue our lectures on the next class.